We're now going to look at one of the classical applications of differential equations, and specifically of linear higher order differential equations. It's important to remember that differential equations themselves were born out of applications first, and the mathematical analysis came second. So this kind of example is what drove the development of differential equations and finding their solutions. The system we're going to look at is fairly simple. We have a mass attached to a spring that's hanging down vertically from some anchor point, and we have this other ingredient here, which is called a dashpot or a damper. And the idea is it is going to add some element of friction into the system. We haven't seen that yet before. Now the system has fairly straightforward physics. It's a pure mechanical system, so Newton's second law, sum of the forces, is going to be our touchstone. What we're going to need to do, though, is define some variables. In particular, we're interested in the position of this mass. If we were to graph over time, we're going to define y equals 0 as the equilibrium point here, and that's going to be relative to the distance away from the anchor point, which is L. Now the nice thing about Newton's second law is it leads straight into a differential equation. The sum of the forces equals mass times acceleration. Well, we're going to move these things around, put the mass on the one side and the forces on the other, because the mass and acceleration are usually the simplest part. If y is a position, then the acceleration is simply its second derivative. And the sum of the forces, well, let's just go through the itemization. We're going to have gravity. We're going to have a force from the spring. We're going to have a force from the damper or dashpot. I'll just use D to be generic. And it's possible someone might be pushing, and it might be up or down. So that would be an external force. That's certainly possible. And we're going to include that for now anyway, as some unknown f of t. We'll call it Fe for F external. Now the nice thing about Newton's second law is we can just itemize all of these various forces and put them into the formula. We're going to have my double prime equals gravity. If positive y is going to be down, we'll define that for a reason we'll see in a second. Mg would be positive. It'll be pulling the positive y direction. Now the spring force is going to be negative k. The k is the coefficient of the spring, so how stiff or how weak the spring is. And the amount of stretch is going to be defined by L plus y. So L's equilibrium length, if y is 0, we would just have a force based on that. And as y changes, we're going to have a different length of the spring. We'll be able to simplify that shortly. The damper involves an interesting force calculation as well. This is one of the friction models that is possible. I actually had a colleague who spent their entire master's thesis looking at other friction models, or actually one other friction model. So this is not universal, but it is something that's typically used, and it's reasonable for most moving objects like this. And the idea behind this is that the friction, or the damping, is proportional to the velocity. In other words, the faster you're going, the more friction there is, and it's simply a scalar multiple of it. Notice the y prime to give us the velocity. And that leaves at the end some other force that we don't know yet. So that's being applied from the outside. And that's really it. We've itemized all the forces. We have a second derivative, we have a first derivative, we have y in here. We have a few too many constants for comfort, so we'll do some rearrangement on the next page. But basically, we're well on our way to getting a second order differential equation that represents the rules of motion for this spring mass system. What we're going to take advantage of next is that at y equals 0, the whole point of y equals 0 being our anchor point is that the spring is in equilibrium. And if that's the case, that means that if we were sitting there, y prime and y double prime would be 0. We would not accelerate, and we would have no velocity. Let's see what that does when we sub all those values in. Y equals 0, y prime and y double prime equals 0. what we're going to have is 0 equals mg minus KL plus 0 plus minus C times 0 and an F external. Well, if we're just talking about equilibrium, we can treat that as 0. We're interested in the what's happening when there is no external force for now. And what that gives us is that mg minus KL is going to equal 0. Using that fact, we get my double prime equals the mg and the minus KL cancel. We end up with a simple minus ky minus cy prime plus F external. And that can be put in perfectly reasonable standard form. What we're going to do is divide through by m. And we're going to bring these two terms to the other side of the equation. And you see what we get with that is just the perfect standard form for a differential equation of second order with constant coefficients. The only wrinkle is that we might have an external force. This is the non-homogeneous part, but only if there is an external force applied. And that's code for if someone's pushing on it or pulling on it, then the physics changes a little bit, obviously, because someone's driving this mass. But if it's just the internal forces, those are all represented in the left-hand side. We have our acceleration related to our damping force, and whoops, we forgot a little, most important, y in the spring force here. And that's it. That differential equation is exactly the kind of thing we've studied how to solve, and it has a little more richness to it than the original model did. It has a friction force, and we can start to do some other work with that moving forward. As an example, let's put some values and see how this plays out in terms of predicting the actual motion of the spring. So we're going to consider a mass of 0.5 kilograms, and we're going to consider a spring constant of 2, and the units all work out to be the standard newtons meters seconds. And it's an undamped, and that translates to 0 damping coefficient. There's no force due to friction. If we go back one page, we're simply going to fill in all the blanks with the values that we have here. Y double prime plus 0 over m times y prime, that's the damping, plus the k over m 0.5 times y, and it's also going to be an unforced system. That means our F external is going to be 0, and at the end of the day we end up with that being 0 on the right, or y double prime plus 4, y equals 0. And this we know how to solve. We're going to do our usual assumptions. Y is equal to e to the RT, and being the independent variable here, we get the characteristic equation. And from the characteristic equation, we find our roots. R squared is -4, so R is going to be plus or minus root of -4. That's better known as plus or minus 2 root minus 1. And we've seen the solution technique for that. Our y is going to be a linear combination, C1 times, what are our two ingredients here? We have an a, which is 0. We have a b here, which is 2. The a is the exponential, the real part goes in the exponent. So we have a to the 0 t times cos of bt, cos of 2t, plus c2 e to the 0 t sine of bt, and that's sine of 2t. And of course, e to the 0 is just 1, so we really just have a simple cos and sine combination. And that is the general solution. So what does that let us do? Again, remember that solutions are equal to predictions. If we're trying to predict what's going to happen to the spring mass, in other words, what's going to happen if we move this thing and let it go, the solution is a prediction of what the position is going to be over time. Now in this particular case, we have a particular solution we're looking for, not the general one, but the solution which satisfies that there's a 0.4 meter displacement from equilibrium at the initial start. So we're going to use that information to nail down what C1 and C2 might look like. The initial condition given is that the displacement, which is y, would be 0.4 meters at the initial time, and we usually define that to be our t equals 0. It wasn't explicitly said, but if you tug on a mass and then hold it somewhere, then let it go, we're also going to assume that the initial velocity was 0. Doesn't have to be the case, but that's usually what we imagine if we're holding a spring mass and releasing it from a stationary position. So what we do is simply use those pieces of information to find C1 and C2. So the first point here gives us that 0.4 has to equal C1 cos of 0, because we're plugging in t equals 0, plus C2 sine of 0. And sine of 0 is 0, cos of 0 equals 1. So we get a really nice equation here, 0.4 equals C1. To get the second value, we're going to need y prime to find C2, because we have an equation for y prime, and we don't currently have it as a formula. So we're going to have to do a quick derivative here. We're going to take the derivative of the general solution. That's going to give us y prime equals C1, derivative of cos is negative sine, and then there's a 2 inside, so we get a 2, plus C2, derivative of sine is cos, and we're going to get a 2 out of that as well. Now we have C1, that's fine, we can use it if we want, but let's just go right now and sub in y prime of 0 equals 0. We're going to have 0 equals, we'll bring the 2 and the negative out front, negative 2c1 sine of 0 plus 2c2 cos of 0. We have that nice property again, sine of 0 is 0, cos of 0 is equal to 1, and out pops 0 equals 2c2. So C2 is going to equal 0. Going back to our general solution, we had C1 and C2 unknown. Now we've solved for them using the initial conditions, and we get 0.4 C1 times the cosine of 2t, and the second value, C2, was just 0, so that term drops out completely. And this gives us the particular solution. And from this, we can actually graph quite quickly and easily a sketch of the position over time. It would be a cos graph, loosely speaking. Let's try that again. Like so. And we could do some other investigations, like finding the period. Period of a cosine is usually 2 pi, but we have a 2 out front, so it would be pi seconds. And so one full cycle here would be about 3.14 seconds to complete one full oscillation. And that would be a graph of y versus t. And so we can predict a number of features. We can predict the amplitude. The amplitude is 0.4. Period is about pi seconds. Well, it's exactly pi seconds, around 3.14 seconds. And we can predict that in the absence of friction, which we assumed, this oscillation would go on forever. So again, we see that idea of the solution being the prediction of what's going to happen once the system is let loose.